Hello, I'm Amma Cranton, and I'm here to talk about our paper, Relative Survivable Network Design. This is joint work with Michael Dinitz at Johns Hopkins and with Guy Kortzarts at Rutgers. All right, so graphs can represent computer networks. In particular, graph vertices and edges can represent terminals and communication links that can fail for any number of real-world reasons. And we may want to build a network that is guaranteed to still function a certain way or maybe maintain a certain property, even after some bounded number of objects in the network fail. In this talk, we'll focus on edge fault tolerance in graphs. So edge fault tolerance is the idea that if up to k edges in the graph fail, then certain node pairs in the graph that we specified ahead of time will still be connected. All right, so edge connectivity. Edge connectivity problems, which can also be seen as edge fault tolerance problems, and I'll explain why that is shortly. Edge connectivity problems, however, have been studied quite extensively. So think like MS or minimum spanning tree problems, Steiner forest, Steiner tree problems, etc. One of these classic edge connectivity problems is the minimum k-edge connected spanning subgraph problem, or KECSS, which we have defined here. So this problem, we're given an input graph, we're given edge weights and some non-negative integer k, and the goal is to find a minimum weight spanning subgraph such that in the subgraph there are at least k edge disjoint paths between every pair of vertices. So the KECSS problem is an edge fault tolerance problem because KECSS is equivalent to asking us to find a minimum weight subgraph such that if you remove any set of up to k-1 edges from the graph, there's still a path between every pair of nodes in the remaining residual graph that you get after removing your k-1 edges. And also notice that the edge fault tolerant interpretation of this problem looks at k-1 faults, while the connectivity interpretation wants k edge disjoint paths. So there's this off by one difference in the interpretations. On the right here, I have an example instance of KECSS with k equals 2. This means we need to find a min weight subgraph such that if any single edge is deleted from the subgraph, then what's left over is still connected. So basically, no single edge should be able to disconnect our solution subgraph. So for this example, we have a solution here in purple. If you delete any edge from this purple subgraph, then the rest of the graph is still connected. Okay, so we also have the survivable network design problem, or SND. Again, we're given an input graph and edge weights, but this time we're given a demand set. This demand set specifies for each vertex pair Si and Ti, there is a demand Ki. The goal is to find a min-weight spanning subgraph such that for each vertex pair SITI, so yeah, for each SITI, there are at least Ki edge disjoint paths from Si to Ti. And note that the KECSS problem from the last slide is actually a special case of survivable network design, because basically if all of the KIs have the same value for all vertex pairs in the graph, then you just get the KECSS problem. As before, this is also an edge fault tolerance problem, since it's the equivalent to asking that for each vertex pair Si and Ti, if we delete ki-1 edges from the graph, then Si and Ti should still be connected. And so again, I have another example, this time for survivable network design. This example is slightly tweaked from the last example. So for one specific vertex pair, S and T, we have a demand of 3, and then for all other vertex pairs, we have a demand of 2. So with this demand of 3, that means that if we remove any 2 edges from our solution subgraph, then S and T should still be connected. And here in purple, we have a solution. If we delete any 2 edges from this solution subgraph, then S and T are still connected. And then likewise, if we delete any single edge from this graph, then all the other vertex pairs are still connected. All right, but unfortunately, there is actually a significant limitation to these edge fault tolerant problem definitions. Suppose this graph here is our input graph for KECSS with k equals 2. So that means we need to find a subgraph such that if we delete any single edge, the graph is still connected. But hopefully you can see that that's impossible because this red edge here is a cut of size 1, and so deleting it separates the graph. So there's straight up just no solution to this problem. However, that feels kind of silly. So why is that? Like, okay, we can agree that deleting this red edge disconnects the graph. And so, okay, it is impossible to return a solution subgraph that can tolerate one edge fault everywhere. However, if you delete any other edge from this input graph, then the graph is still connected. So yeah, the graph can't tolerate all single edge failures, but it can tolerate a lot of them. Actually, it can tolerate all of them but one. So it seems kind of silly to not just return anything at all, right? Okay, fine. Maybe instead of trying to solve k equals 2, since we can't do that, what if we maybe bring k down 1, so set k equals 1, and then return a solution for KECSS when k equals 1. Here's what that solution looks like. I would argue that this is an unsatisfactory solution, and here's why. So our original graph is really close to tolerating all size 1 edge faults. However, now this KECSS solution for k equals 1, this solution subgraph is not even remotely close to tolerating all size 1 edge fault sets. Actually, it tolerates none of them. So by solving for k equals 1, we've actually lost a ton of connectivity that we originally wanted, since remember we were asking for k equals 2. Now we're not even close. So I have what we claim is a valuable solution to these issues. So what if maybe instead of what we've tried, we try to return a subgraph that can tolerate the fault sets that the original input graph can tolerate? So for example, the input graph gets disconnected when you delete the middle bridge edge. So we shouldn't be mad if our solution subgraph is also disconnected when you delete it. However, the original subgraph isn't disconnected when you delete any other edge, so maybe we should ask for a solution subgraph that also isn't disconnected when you delete any other edge. If we ask for these things, we get this solution here, this green subgraph. So of course, this is not a solution to KECSS with k equals 2, and it's not an optimal solution for KECSS with k equals 1, since there's some extra edges here. However, the subgraph is in a sense a relative solution for k equals 2. For any edge fault set that has size 1, if that fault set disconnects the graph in the input graph, then it also disconnects our solution here, which, duh, we can't do anything about that. But for any edge fault set that has size 1 that doesn't disconnect the input graph, it also doesn't disconnect this solution subgraph here, right? If you delete any edge from the solution that isn't that middle edge, then our green solution subgraph stays connected. Okay, so to summarize, all of the edge connectivity problems we've discussed before now are absolute fault tolerance problems, in the sense that they ask for these absolute properties with no consideration as to whether the input graph even has those properties to begin with. Yeah, so what happens if the input graph doesn't have those properties? Then, well, we get no solution, and that's not very useful. So to state all this a bit more formally, with absolute fault tolerance, we're asking for SI and TI to stay connected after removal of any set of KI-1 edges. And again, notice that this demand does not take into account the fault tolerance of the input graph. And then with our idea of relative fault tolerance here, we only demand fault tolerance when we know G itself has enough connectivity to tolerate those faults. And a very important note here is that relative fault tolerance is actually a generalization of absolute fault tolerance, because these two definitions are actually the same when the input graph already has the desired connectivity. All right, so now with this idea of relative fault tolerance, we can create new problems by applying this idea of relative fault tolerance to these absolute fault tolerance connectivity problems. So first we have the k-edge fault tolerance spanning subgraph problem, for the KEFTS problem. As always, we're given an input graph and edge weights, and we're also given a non-negative integer k. The goal is to find a min weight spanning subgraph such that for any fault set, which we call f, so any such f that contains at most k minus 1 edges, then if a node pair is connected in G minus F, then that same node pair is connected in H minus F. And of course, if the node pair isn't connected in G minus F, we don't expect anything. Yeah, also note that this KEFTS problem is a generalization of KECSS. So if the input graph to a KEFTS instance does actually have k edge disjoint paths between every pair of nodes, then the problem is exactly just KECSS. On the right, we have an example. The input graph is the same as the one we looked at a few slides ago when we were discussing the issues with absolute fault tolerance. So now we want to show here that we no longer have those issues. Here is a solution to this KEFTS instance with k equals 2. If you remember, this is the solution we proposed a few slides ago, actually. And yeah, we get a useful solution. With this new problem definition, there is always a solution, and that's nice. Next, we'll do the same thing with survivable network design. Now we have relative survivable network design, or RSND. We're given an input graph, weights, and a demand set, which specifies a demand for each vertex pair. We want to find the minimum weight spanning subgraph such that for all vertex pairs Si and Ti, and fault sets F, where F has size at most Ki minus 1, if there is a path from Si to Ti in G minus F, then there is also a path from Si to Ti in H minus F. So if all the Ki's have the same value, then this is just the KEFTS problem from the last slide. And then also note that RSND is a generalized version of SND. Again, I have an example on the right. This is an instance of RSND, and we have a demand 3 from S to T and a demand 2 for all other vertex pairs. So here in green is an RSND solution to this instance. For any edge fault set F of size 2 or less, if S and T are connected in G minus F, minus those two edges, then they're connected in this green solution, minus F. And then the same thing is true for fault sets of size 1 or less for all the other vertex pairs. And yeah, if this was an instance of normal survivable network design, then there would be no solution to this because there's only one edge disjoint path from any of the vertex pairs that are separated by this middle bridge edge that's like a size 1 cut. And I want to stress that these are new problems. These definitions feel pretty natural, but despite that, at least to the best of our knowledge, these problems haven't been studied before. And now we have our results. So yeah, we've defined some new problems and we came up with some results for them. We give a 1 plus 4 over k approximation for unweighted KEFTS. So that's when all of the weights are 1. We give a 2 approximation for general KEFTS, so for any weights. We also have a 2 approximation for the 0, 1, 2 RSND problem. So this is a special case of RSND when all of the pairwise demands are at most 2. So basically they're either 0, 1, or 2. Yeah, feel free to check our paper for details. I won't go over this result in our talk. I also won't go over this next result in our talk, but we also have a 27/4 approximation, and which is 6 3/4 for single demand RSND for k equals 3. So this is another special case of the RSND problem, and in this case, only one vertex pair has a non-zero demand. All other vertex pairs have demand 0. This seems like it should be a relatively simple special case since there's only really one demand, but we found that even when there's only a single demand, and when that single demand is just 3, it was still surprisingly difficult even to just get this 27/4. And yeah, again, you should check the paper for details. As a whole, though, I want to emphasize that our main contribution is this new notion of relative fault tolerance we have, particularly for edge connectivity problems. Okay, so first of all, it turns out that survivable network design can actually be written as a cut covering problem. So we have this vertex cut function defined here, f s and d of s, and this cut function is defined over all vertex subsets of the graph except for the empty set and for the entire set of vertices. Um, and the S and D problem is equivalent to finding a min-cost subgraph such that in every cut of the solution subgraph, there are at least f of s edges going across that cut. After some thought, it's not too hard to see why this is true, like why this is equivalent, but we won't go over why in this talk for the interest of time. Right, so with this cut function, we can write the survivable network design problem as an integer linear program, and this is what it looks like. And yeah, of course, we can do the same thing with the KECSS problem. The cut function is much simpler, and the LP is very similar. This is what it looks like. And now we define this property of vertex cut functions called weak supermodularity. So a cut function is considered weakly supermodular if one of the following inequalities holds for all vertex subsets A and B. Either f of A plus f of B is at most f of A minus B plus f of B minus A, or f of A plus f of B is at most f of A intersect B plus f of A union B. Okay, so in a seminal paper, Jane introduced the iterative rounding technique for solving linear programs. Jane showed that for a cut covering problem like survivable network design, if the cut requirement function f of s is weakly supermodular, then you can use iterative rounding on the corresponding linear program to get a 2 approximation for the problem. The survivable, and yeah, fortunately, the survivable network design cut function is weakly supermodular, so you do get this 2 approximation. And then in a follow-up paper, Gabot and others observed that the techniques used in Jane's paper directly imply a 1 plus 4 over k approximation for the unweighted KECSS problem, and they make the observation that you can do this with like a much simpler threshold rounding scheme. All right, now we can finally start talking about KEFTS. And remember that the KEFTS problem is the problem we came up with by applying relative fault tolerance to the KECSS problem definition. Okay, so with KEFTS, we first tried to do the same steps that Jane took for survivable network design. We first tried to write KEFTS as a cut covering problem, and then of course the hope is that the cut function for KEFTS is weakly supermodular, because if it is, then we can use iterative rounding and get that 2 approximation. So we found there's actually more than one cut function that captures the KEFTS problem, and we defined and tried out a few of them, but it turns out the ones that we tried out were not weakly supermodular. So I'm now going to talk about the cut function we did end up using and briefly explain why and how we used it. So to define the cut function that we used, we define what we call forced edges. If an edge goes across a vertex cut that has size k or smaller, so if this vertex cut has at most k edges going across it, and there is an edge in that cut, then that edge has to be in any feasible solution. That's why we call them forced edges. So we can remove these edges from the input graph as a sort of pre-processing step, and we can solve the residual problem. The cut function we have is defined here, ff of s. I won't go over why this works, but again, it's not like too hard to see after some thought. All right, so we've defined this cut function. It captures the problem. So the hope is that it's weakly supermodular. Actually, unfortunately, it's not. but maybe that seems strange at first because I did just say that we tried some other cut functions that also capture the problem and that those cut functions weren't weakly supermodular. So like, why is this cut function special if it's also not weakly supermodular? So we observed that the weak supermodularity property that Jane relied on for iterative rounding is a sufficient but not necessary condition to be able to use the techniques from that paper. So remember that with weak supermodularity, we have that a property holds for all pairs of vertex subsets. However, we noticed that Jane never needed the cut function to be weakly supermodular on for all pairs of vertex subsets. Instead, weak supermodularity was only being used for certain special vertex subsets. And if you want more information about like what what properties these special vertex subsets have, feel free to check out our paper. But anyway, fortunately, we found that this cut function we just defined, ff of s, does actually satisfy the weak supermodularity condition on these special vertex subsets. And so we say that ff of s is locally weakly supermodular. So for general KEFTS, the cut function is locally weakly supermodular, and we proved that that is enough for us to use Jane's results to get a 2 approximation for general KEFTS. For unweighted KEFTS, we showed that with local weak supermodularity and with some tweaks of the argument in the follow-up paper by Gabot and others, we get a 1 + 4 over k approximation for unweighted KEFTS. Oh, and interestingly enough, I should emphasize, at least as far as we know, this is the first use of Jane's iterative rounding techniques that don't use a weakly supermodular cut function. Okay, so, and finally, we have some open problems to leave you with. So we do not have any algorithms for general relative survivable network design. We tried a bunch of cut functions that capture the RSND problem, but we found that none of those cut functions were weakly supermodular or even locally weakly supermodular. So maybe some other approach is needed here or some other technique is needed. And then for single demand RSND, I did briefly mention in our results section that single demand RSND for k = 3 was surprisingly difficult. So this special case feels like a difficult problem, but we don't actually have any hardness results to back up that hunch. And then for k = 3 single demand RSND, we have that 27/4 approximation, but it seems very plausible that like with a different approach, you could improve this ratio. And then finally, we have vertex relative fault tolerance. I didn't even talk about vertex relative fault tolerance at all in this talk, but there are many, many interesting problems in this space that are like the analogous of the edge connectivity relative fault tolerance problems. But yeah, we didn't look at it in this paper, but definitely a lot of interesting problems there. Thank you for listening.